Hi there. In this video, we're going to talk about double integrals over general regions. So in the previous video, we looked at double integrals over rectangles. And in fact, this is the double integral that we looked at. We found the double integral over that rectangular region right here, right? And we ended up computing the signed volume of this chunk of stuff over here. And of course, it's below the xy plane, so the volume ends up being negative. We worked that out in the last video. So what we'd like to do in this video is look at the case where this region here is not necessarily a rectangle. Okay, so let me put in some curves to describe what this region is. All right, so here's our new region. So in this video, we're going to be looking at how to find the integral over this shaped region here. Now, if you look at it in the xy plane, if I pull this out, you can see it a little bit more clearly from above. So we are between this curve, and this curve, and that defines our region. It's like a slanted ice cream cone. All right, so that's what we want to integrate over. Okay, so let's see how we can do this. Okay, so here's the integral that we want to do. We want to integrate this function over the region R with respect to area, right? Where R is the region bounded between these three curves. Those are the three curves we saw in the picture here. We have the curve x equals -1, y plus x squared equals 1, and y plus 1 equals x right there. Okay, so that's the integral that we want to do. Now, remember, we can use Fubini's theorem for these. Okay, so I need to decide whether to split this up dy dx or dx dy. All right, so I'm either going to do this integral or I'm going to do this integral. Okay, now I have to decide which one is the one that's more appropriate here. Now, let's think about what happens here. When we do these integrals, when I do this integral over here, for instance, I'm going to be integrating this thing on the inside, right? And I'm going to do that for every single value of y. All right, so that means that my bounds for x here, for every value of y, they could depend on y. All right, because in the next step, I'm going to integrate out the y's. Okay, so those bounds could depend on y. Now let's see what functions of y they might depend on. Okay, so let's go look at the picture and see how that's going to pan out. So for each value of y, I'm going to integrate x from some value to some value. Now, I can see here that for each value of y in this region over here, I'm going to evaluate x from this curve up to this curve. Now, as I come along here, when I get down to here, I'm going to evaluate the integral from this curve to this curve. Notice that the curves changed. On the one hand, in the interval 0 to 1, from y equals 0 to y equals 1, I'm between these two curves, whereas on the interval -2 to 0, I'm between these two curves. That means that if I'm going to do the integral this way, I'm going to have to split it up into two separate integrals. One where I use these curves as my bounds, and the other one where I use these curves as my bounds. Okay? Now let's look at the other one. Okay? Let's look at when we do dy dx. So I'm going to do this inner integral, and that's for each value of x. So for each value of x, I'm going to integrate with respect to y, and I need to find the things that go here and here. Let's see how that's going to pan out. So for each value of x here, between -1 and 1, I'm going to go between this curve and this curve. Notice that it's always between this curve and this curve. I don't switch. I don't have to stop using one curve and switch to another one. The bottom curve is always this one, and the top curve is always this one, unlike the way we tried to do it in the first attempt, right? So that means that this one's going to be much more straightforward. I won't have to split it up in terms of two integrals. So that means that in this particular case, this is the much better approach to solving this problem, dy dx. And that's because for each value of x, there's only one pair of curves I have to go between for the span in the y direction. Okay, let's think about what those are going to be. Okay, so for each value of x, x is going to go from -1 to 1. Okay, well that right there actually tells me what these outer bounds are, right? dx, that's the outer integral, so that's going to go from -1 to 1. So that's how I'm going to set this up. So the outer integral is from -1 to 1. Now what does y go from? Well, y is going to go from this line, right? That's the lowest that it gets, up to this curve up here. So these aren't just going to be numbers, they're going to be expressions. They're going to be values that depend on x, so they're going to be expressions in x. See, depending on what x is, I'm going at a different, I'm spanning a different interval. So these are going to be expressions involving x. What are these expressions? Well, they came from the curves that we were given. The bottom curve, this straight line, is given by this. Y plus 1 equals x. That's what defines this line right here. That is the lower bound for my y's, right? So I'm going to want to put that somehow down here. Now for each value of x, I want to have an expression, a value down here that I start at. So it should be an expression in x. So I should solve this for y, right? So if you solve that for y, you get y equals x minus 1. That's what goes down here, x minus 1. So for each value of x, I know exactly what number this is going to be. Now what about the upper limit? Well, that's this curve over here, and that came from this expression. So if I solve this for y, I get y equals 1 minus x squared. So that's what goes here, 1 minus x squared. Okay, so let's go ahead and do this integral now. Okay, so to do the inner integral, we're going to antidifferentiate with respect to y, treating x as a constant. Right? That means all this stuff out here is a constant. So I just antidifferentiate the y part, and what do I get? I get 1/9 x minus 1 y cubed. And I'm going to evaluate this from x minus 1 to 1 minus x squared. And then I'll do my x integral. Okay, so I'm going to plug in this for y and then subtract what I get when I plug in this for y. Okay, so now I have my integral involving x. So I'll integrate this. Now, to integrate this, I'm going to have to probably, I think it'll be easiest to expand everything out. Okay, so let's expand all this out, and what you get, I did this ahead of time. And actually, while I do this, I'm going to pull this constant of 1/9 outside the integral. All right, now this looks nightmarish, right? This looks like it's going to be a pain in the butt. But it's really not that bad. Some of these functions are odd functions. An odd function is a function f of x where f of negative x is equal to negative f of x. All right. So what that means is that the function is the negative to the left of the y-axis as what it is to the right of the y-axis. And what that means is that if we integrate from -1 to 1, or minus a to a, we always have an equal amount of negative area to the left of the y-axis as positive area to the right. So those areas cancel off. So if I ever integrate an odd function from minus a to a, in this case -1 to 1, I get 0. So all these odd terms are going to integrate to 0. I can see that right off the bat. So really all I have to do is integrate the even parts. Okay, so I'll just antidifferentiate those. And I'll be evaluating those from -1 to 1. All right, so if I plug in 1 into this stuff, I'm going to get negative 128 over 35. If I plug -1 into that, I get positive 128 over 35. I do that subtraction, multiply by 1/9, and I get negative 256 over 315. Okay, that's my answer. Now it's a negative quantity. Does that make sense corresponding to the picture that we saw? Well, let's go take a look. Well, look at that. Look at the thing that we're finding here. Most of it, in fact, all of it, is below the xy plane. Right? So it should be a negative quantity. So what I'm seeing here in my computations makes sense. Now I want to point out how can you tell if you're doing this right? Well, I already pointed out some things. You want to make sure that when you pick the order of integration, you want to make sure that for each value of one variable, you're only going between two particular curves in the other one, right? You don't have to switch from one pair of curves to another pair of curves. That would be the wrong way to do it. If you can avoid doing that, you should. I also want to point out that in the computations here, we had an integral in y, and we had expressions in x over here. That will always be the case. This variable that appears in the bounds should never, ever match the variable that is over here. So it would be wrong to put expressions in y. Why is that? Well, because if I were to integrate to y and I evaluated at functions of y, I would be left with a function of y. My next step is to integrate with respect to x. But at that point, that means the y's will never go away. So in my answer, I'll end up with variables y. That doesn't make any sense. I should be getting a number as an answer. So these really can't be functions of y. And similarly, these values that come on the outer integral have to be numerical, because at the end, it can't be left with variables. I should be getting a number as an answer. And so these should not be expressions of x or y. These should simply be numerical values here. So numerical values always on the outer integral, and expressions not of this variable on the inner integral. They will always be expressions of the remaining variable or variables when we get to three-layer integrals in the future.